Now then, we're looking at section 12.8, second order derivatives. And here's the idea. First of all, I'm just going to show you something about this notation, this dy by dx. Now that comes from, if you remember, delta y divided by delta x, change in y divided by change in x. But that's no longer how this notation works. In fact, we should think of it like this. Or we could think of it like this, rather. We could think of it as d by dx tells us do differentiation and do it to this function y. Okay? So I'm doing differentiation on this function y. So I take a function and I apply differentiation to it and it gives me a different function. So for example, if I did d by dx of x squared, that is telling me differentiate this function here, differentiate that function there, and that gives me 2x, okay? So I take a function, I apply this d by dx thing to it, and what I get out is the derivative, is the first derivative, it's the gradient function, okay? So that's where the notation that's how the notation can be used now, okay? It comes from delta y divided by delta x, but what it is now is take a function and apply this thing called differentiation to it, and the way that we apply this thing called differentiation is to write d by dx of the function. And usually the function is y, so we often end up with dy by dx, okay? Now, whenever we have something in maths, we like to repeat it. So we start off with 2 plus 2, and that gives us 4. But then we say, yeah, but what if we did 2 plus 2 plus 2 plus 2? And then we have that repeated addition. Instead of just doing 2 plus 2 once, we do 2 plus 2 plus 2 plus 2 plus 2. And then we end up with, well, repeated addition is called multiplication, isn't it? So we start off with addition. We repeat that and we get multiplication. And then we end up with 2 times 2 times 2 times 2. What if we keep timesing 2's together? And then we end up with indices, powers. Okay? So when we have a new idea in maths, we like to ask ourselves, well, what happens if you apply that idea and then apply it again? And that's exactly what we're doing with differentiation. The example they've got in the book is as good as any. Y equals 5x cubed. The derivative, d by dx of y, is 15x squared. And then what if I want to differentiate again? So I want to differentiate the derivative. So I want d by dx of dy by dx. I want what happens if I take this function and differentiate it. Now, we know that if this is the function, this is the gradient function. This is the derivative. It tells us the gradient of this function. What does this second derivative tell us? Well, for the moment, let's not worry about it. I'll talk about it in a moment, but really what's important here, and for this section, the only thing we need to understand in order to be able to answer the questions is, take the function and put it through the process of differentiation, you've got another function. If you've got a function, you can put it through the process of differentiation. And this is what we get, okay? And I could do that again if I wanted. I can keep differentiating. Now, and you may be able to see if I did do that again, I'd get 30, and then if I did it again, I'd get 0, and then I'm just going to get 0, 0, 0, 0 all the way down. But I can differentiate once, or I could differentiate twice, or 3 times, or 4 times, or 5 times. I've got a mathematical process, so I can repeat it, okay? If I do it twice, then this thing I'm going to call a second order derivative, and this notation for it, instead of writing d by dx of d by dx of y, we're going to write that as this, which is pronounced d2y by dx squared. Okay? Don't ask me why, that's just the notation that I was taught, that's the notation I'm now teaching you, that's the pronunciation I'm now teaching you. The notation sort of makes sense, doesn't it? It's the d by dx twice. The way we say it is d2y by dx squared. Don't know why it's a 2 in one place and a squared in the other, but that's what we say. So it's called the second order derivative, and in function notation we just put 2 little dashes there, okay? So you've got a function, we've got a function of x, the first derivative. If you differentiate the first derivative, you get the second derivative. Now you're probably asking, well, what about third derivatives and fourth derivatives and third derivatives in function notation and fourth derivatives in function notation? And you'd be quite right, that is the notation for them. So d4 by dx to the power of 4, and if it's y that we're doing this to, then like that. And same here, just put 3 dashes or 4 dashes or however many you want. Now, that's the notation for them, but we're not going to worry about those. All we need for the moment is to go as far as the second derivative, okay? Now, in terms of interpreting the second derivative, we will use it in section 12.9. I'll do that in the next video. But just to give you a bit of an idea, it doesn't really matter in terms of solving these questions. If all you want to be able to do is solve the questions, I've told you everything, okay? Just go and have a go at them. If you want to understand a little bit about what's going on, then think of it this way. If you have a function, if the function's going up or down, that's what the first derivative tells us. Okay, so if the value of y, if the y coordinate is increasing, then the first derivative is positive. Okay, and if the y coordinate is decreasing, the first derivative is negative. It's an increasing or a decreasing function. The second derivative tells us about the way in which the first derivative is changing. So the second derivative is the rate of change of the gradient. Okay, it's the way the gradient changes as you move. So here, the gradient is positive and it's getting smaller. So the gradient's going down. So at this point, the second derivative would be decreasing. Here, the gradient goes from positive to negative. So the gradient's still going down. So the first derivative, the gradient function, is a decreasing function, and the second derivative would tell us that that function is a decreasing function by being negative at that point. Okay, so you can think of it as the rate of change of the rate of change. It's the rate of change of the gradient. If you want it in a sentence, the second derivative tells us whether the gradient of the function is increasing or decreasing. Okay, again though, don't have to worry about that at this stage if you just want to answer the questions. Even if you do want an intuitive understanding of what's going on, it may be a good idea to just stop and answer the questions and get to grips with the algebra and the nuts and bolts of doing the sort of problems they set you first, and then come back to it later and think about what it signifies. Very quickly, just to tie this together with some of the mechanics work, if you've got S for displacement, or distance if you like, the rate of change of distance is velocity by definition, okay? And if you think about that, if your position is moving, you have a velocity. If your position is moving quickly, you have a high velocity. If your position is moving slowly, you have a low velocity. So the way in which velocity changes over time is called velocity. If your velocity is changing over time, well, a change in velocity is an acceleration. So an acceleration is what we get if we differentiate velocity over time. So the second derivative of displacement with respect to time is acceleration, and I should be calling these vectors, shouldn't I? So I'll underline them. Okay, so there's another sort of intuitive idea about second derivatives, but not to repeat myself too much. If the intuition as to what's going on is worrying you, for the moment, ignore it, just have a go at the exercise. Okay?